Now, I would like to say a few things about particle accelerators. And in the meantime, I'm going to describe the working principles of the cyclotron. This is one of the types of accelerators that we use. But first, let me start with these simple questions. Why do we accelerate particles? There are many reasons for that. We use these fast particles for many measurement processes, but they are especially used in experimental particle physics, where you collide particles with high energy, and as a result, new particles emerge from as the collision products. These particles have high masses, so as a result, to be able to produce them, you need very energetic particles. So as a result, that's why you need to give them very large energy. So to be able to produce new particles with even higher masses, of course, you need to give more energies to these particles. That's why people are building accelerators with higher and higher energies. Okay. Then the next question is, how do we accelerate particles? Obviously by applying forces on them. But if you think about it, if you think about the four types of forces of nature, there's only one of them that you can really use. Weak force and the strong force, they are out of the picture because you cannot manipulate them easily. Gravitational force is usually weak on particles of atomic scale. So as a result, there's only one option in here. You can only apply electromagnetic forces. So somehow you apply some electric fields and magnetic fields. By using these, you can manipulate these particles. So because of this fact, there are these two things which emerge, which is kind of a necessity. You need to accelerate charged particles because you cannot apply an electromagnetic force on neutral particles. Sometimes for atoms, of course, atoms are composed of charges. So as a result, there are some, it is possible to apply some forces on atoms, but these are usually weaker compared to the forces that can be applied to the charged particles, right? So that's one requirement. The particles should be charged. So the electrons, protons, or ions, these are the ones that we accelerate. And the second thing is that, of course, we always should have an electric field because only the electric fields can exchange energy directly with the charged particles. So somehow your design of the accelerator should contain an electric field. Apart from these two details, all the other details of the accelerators may change. So there are many designs. So I'm going to explain first in here the simplest possible thing that you can do. This is what Thomson has done when he tried to measure the properties of the electron. So this is a device that has, you can think of it as two stages. There's a device that's called the electron gun in here. It's usually a metal with a sharp tip. It's also usually heated so that the ejection of the electrons from the tip becomes easier. And of course, you apply a large negative potential. You apply a potential difference between the tip and some other plate in here so that the electrons are more readily ejected from the tip. Right? That's the first stage. Usually you get a beam of electrons, lots of electrons moving with different velocities in here. Some of these electrons will be captured by this plate, but usually have a small opening in here so that some of the electrons pass through. Right? In that case, we pass to the second stage where we accelerate the electrons. This is actually two plates. This is actually a capacitor arrangement. These two plates, the first plate should be negatively charged and the second plate should be positively charged. So as a result, there should be an electric field between the plates. I'm going to show the electric field with a blue color. So from right to left in that situation. In that case, the electrons will be accelerated towards right. Okay, so how much would they be accelerated? Sorry about this. Let me do a simple, write down a simple expression for it. So let's say that when the electrons emerge from the first hole, let's say that let's just think about a single electron. Let's say that its initial velocity is v0 to the right, and we would like to find its final velocity. So what happens in here? Well, basically, the potential energy changes, but let's remember our basic principle. The total energy of the electron is conserved, so therefore the change in the total mechanical energy is zero. So that means the change in the kinetic energy plus change in the potential energy is zero. So what happens in here is that the potential energy decreases, so this is negative, and therefore the kinetic energy increases. How does the potential energy change? Well, it is the charge of the electron multiplied with the change in the potential. So since I'm applying a potential difference of V, this is the battery that applies this potential difference. So therefore the change in the potential would be positive V, and so therefore the change in the potential energy is a negative EV. So therefore the change in the kinetic energy would be positive. So in this process, therefore, the electrons will gain, every electron will gain a kinetic energy of E times V. And that's also why the electron volt unit is handy, because you can easily calculate the change in the kinetic energy, right? So most of the time, of course, in the second stage, you apply a bigger potential difference in here. So this is really large. So as a result, the initial kinetic energy of the electrons are kind of unimportant. So as a result of that process, you may say that the final kinetic energies of these electrons are of the order of EV. Okay. So that's the basic design. So this is, therefore you get a beam of electrons in here, or beam of charged particles in general, where you can use in your experimental procedures. The next question is, can we accelerate these particles more? Because usually you get some kinetic energies in here, but most of the time this is not enough for you. You would like to accelerate them more. So what can you do about it? There are many possible designs, actually. Let me add a new page in here and try to explain some of them. You can actually use this accelerating plate arrangement many times. That's one possibility. But I'm going to first concentrate on this other design, where let's say that you have an electron in here where initial speed is v0. You have accelerated it in between the plates, so when the electron went out from this other hole, it has a higher speed. Okay, so let's just think about a possible design where you have some mirrors in here. So I'm just going to show them like that. First, let's just not think about how we can build these mirrors, but let's place these 4 mirrors in here so that this electron gets reflected from these mirrors and then comes back to the initial point that it has entered into this region. So as a result, in this process, therefore, I can accelerate the electron even more, and then in the second stage, of course, it's going to have a higher kinetic energy. So let me kind of write it down like that. So this is the initial kinetic energy, let's say, of the electron. When it has accelerated, it has gained a kinetic energy, which is initial plus the EV. And then it has, of course, reflected off the mirrors and then came back to this initial point again with this kinetic energy. And then it will accelerate more and so on, right? So therefore, it's going to have a 2 EV energy and 3 EV and so on. Is this going to work? That's the first question I would like to ask. All right, I want you to think about it. Since I'm asking this, it should be obvious that it's not going to work, but why shouldn't it work? Let's remember the whole argument again. So let me use a yellow color in here. We have used the conservation of energy in here. So the electron has a initial potential energy in here and a final potential energy. And what we have done is we have just used the fact that the change in the kinetic energy plus the change in the potential energy is 0. So what happens is that when the electron moves from this initial position to that final position, the potential energy decreases, therefore the kinetic energy increases. That is how we have made sure that it accelerated. We have given energy to it. But if you think about this process where it moves from this point back to the initial point, whatever the path is, it doesn't matter. The potential energy will increase, so therefore the kinetic energy should then decrease, right? So as a result, somehow this bouncing of the mirrors is not a simple process. There is no such thing. And we can also understand the physical reason why this is the case, because we have talked about that. We have said that, well, in this kind of an arrangement of capacitors, where this one is the positive plate and the other one is the negative plate, there's an electric field between the plates, but there's also a fringe electric fields outside, right? These are usually weak. Since they are weak, we neglect them, but they are present, because if I want to compute the potential difference between the plates, I can compute this potential difference as the integral of the electric field, but my expression should not change depending on which path I follow. So as a result, if I move from this point to that point, following that path, I would get a certain potential difference. It's basically electric field multiplied with the distance. But I can start from the same point but follow the other path like that and integrate the electric field. Again, I should get the same potential difference. So this shows that there's an electric field also outside. So you can see, understand the reasoning here. So in this stage, electrons are moving against the electric field. So therefore, the force on them is parallel to their motion. So therefore, they speed up, right? But in this stage, they are moving parallel to the electric field. So therefore, the force applied on them will be opposite to their motion. So therefore, they are going to slow down. So as a result, as long as the electric field in here is static, this design is not going to work. However, this design will work. So instead of applying a DC potential difference between these plates, you apply an AC potential difference, an alternating EMF. In that case, the direction of the electric field between the plates is going to change periodically. So sometimes it's pointing towards left and sometimes it's pointing towards right. So by adjusting, of course, when to send the electrons, you can make sure that they always accelerate. So there's some kind of a design like that, where, let's say it like this, when the electrons are in here, somehow you adjust the AC field in here such that the electric field is pointing towards left, all right? So as a result, when the electrons are moving, of course, they will accelerate. And then, of course, you just reflect the electrons and send them back to the same region again, probably through the different holes. And of course, and at that time, of course, they are going to see reverse polarity. So as a result, when they are passing between the plates, they are going to accelerate again, and so on, right? You can, by using a time-dependent potential difference across the plates, you can basically accelerate them in such a way that they always gain energy. So that's the key principle in here. So we cannot use a static electric field. We have to use a time-dependent one. The second detail in here, there are no mirrors. We have said that there is no way of applying forces to charged particles except the electromagnetic ones. So as a result, instead of mirrors, of course, we need to use magnetic fields, right? So somehow we have to apply magnetic fields in here. And we know that inside magnetic fields, the charged particles bend. So as a result, just make sure that these electrons or the charged particles bend like that. So as a result, this is going to play the role of a mirror, essentially. So the whole purpose of the magnetic field in the accelerators is to just basically guide the particles so that they can pass over and over again from the same places. Okay, but this is the only function of the magnetic field. The function of the electric field is to give energy to the particles, and you would like to make sure that when the particles are passing from that region that you are going to do the acceleration, you just choose the direction of the electric field correctly. Okay, so the cyclotron is a device that actually uses more or less the same kind of a principle, except that we don't have this parallel plate arrangement in here. It's a different kind of an arrangement. So the arrangement is something like this. There's somewhere in here, there's a picture, yeah. That's the cyclotron picture. Let me try to describe the design in here. We have, first of all, a magnet. So that's the north pole and that's the south pole of the magnet. So it's just a circular magnet to obtain high magnetic fields. People use electromagnets, of course. So we are going to assume that with this magnet, we can obtain a uniform magnetic field in this gap region in here. And this is where we are going to do the acceleration process. So instead of a parallel plate capacitor, we have 4 metallic plates, and each one has the shape of D, letter D, and that's why they are called Ds. They couldn't come up with a better name for that. But in any case, they are arranged like that. There are 4 of them. So on the right, I show the top view in here. So as a result, a single D in here. So that's the plate in here. But there's a plate below that, which is parallel to that. Okay. So next, what you do is you just connect both of these plates, which are on top and down, to an AC potential difference, so that you maintain a potential difference between the 2 Ds on the left and the 2 Ds on the right. Okay. Since let me try to show it like this. I'm going to use a green color in here. Let me show this top D and the D below, right? They have the same potential, so therefore there is no electric field within that region, right? And so as a result in here too, right? In that region there is no electric field. No electric field in the horizontal direction or the vertical direction. So as a result, the particles in here would be moving with constant speed. But of course, they are going to follow a circular trajectory because of the presence of the magnetic field. But they won't be accelerating within that region. So let's keep this in mind. And it's similarly the case for the other region. But there's an electric field between the left Ds and the right Ds. So there's an electric field in here. Right? I'm just going to show these two, but there's a constant potential difference between the 2 Ds on the left and the 2 Ds on the right. And so as a result, when a charged particle passes from this region between 2 Ds to the other region, they will either accelerate or decelerate depending on the direction of the electric field. Some of them are going to slow down. The ones that are slowing down, we don't care about them. But the ones that are speeding up, these are the ones that we need. So what we would like to do is basically bend the particles in such a way that when they come back and then pass from this region again, we would like this electric field to be pointing in the opposite direction. So as a result, when they are passing through this gap region in the second time, we want to make sure that they accelerate again. Okay, so the only way that we can do this is to make a match between the frequency of rotation of the particles in here, which is the cyclotron frequency, and the frequency of that AC EMF device. So we would like these two frequencies to be the same. So that's the essential idea in here. And that's why this is called the cyclotron frequency, because it's the frequency that actually you rely on when you are building the cyclotron device. So let's remember the frequency in here, the expression. So the charged particles inside a uniform magnetic field, they are going to do a circular motion. The angular frequency of that circular motion is given by this expression. We have charge to mass ratio of the charged particles. So that is going to depend on the type of the particle. So if you want to accelerate electrons, it's going to be a different quantity. So you need a different design for different particles, of course. So it depends on the charge to mass ratio and the magnetic field. But apart from that, it doesn't depend on the energy of the particles. So as a result, however you accelerate these particles, this frequency is going to be the same. So therefore, you apply the same AC frequency to that device. So let's just go over the motion from the example of protons. So the usual slow source of protons is at the center. So suppose that we have obtained a single proton in here, which is moving like that. Okay, let's describe the motion. So the magnetic field in here is pointing out of the paper or out of the screen direction. Velocity is to the right, so therefore V cross B is downward. So let me just show it at least in here. So this V cross B, this is pointing downward. Since this is a positive particle, therefore the force is also in this direction. So therefore the acceleration is in this direction. And so therefore this is going to follow a circular path like that, right? So it's going to be circular in any case. Of course, this is a constant speed motion in here, but when the particle is passing from this gap region, it's going to speed up. So therefore, speed will increase. Let's remember what the radius, how the radius depends on the speed. If I remember this correctly, so it's the mass divided by QB times the speed. Yeah, that must be the correct expression, because this is like V divided by the cyclotron frequency, and we have said that the V is equal to omega times R is the relationship between the rotational and kinematical quantities. I'm relating the angular velocity to the linear velocity in here, right? Let's just remember these. So in any case, so the radius of the motion is proportional to the speed of the particle. So as a result, when the particle passes to the other side, it's going to have a higher speed. And so therefore, it's going to follow a path with a bigger radius. And so as a result, it's going to come back in here. When it is passing from the gap region second time, of course, it's going to speed up. So it's going to have a bigger speed in here, and so therefore it's going to follow a bigger trajectory, a trajectory with a bigger radius, and so on. So therefore, this particle is going to do the spiral-like motion. Well, eventually, of course, it's going to get out of the device. Okay, so in all of these processes, this is the initial speed. After the first acceleration, it's going to have a bigger speed, and so on. The speed also increases. But at each time, of course, when it is passing from this gap region, its kinetic energy increases by basically its charge multiplied with the potential difference at that time, right? So as a result, the kinetic energy at each step increases by the same amount. Okay, we can also guess and find what the final kinetic energies are. So at this stage, of course, when the particle emerges from this beam, so that's the final speed, the final radius of the circular motion, therefore, is equal to m divided by q times b times the final speed, all right? So basically, I mean, since you have just produced the particle at the center, so its radius continuously has increased. Of course, at some stage, the radius would reach to the value which is equal to the radius of the device, right? That's basically is given by the size of the electromagnet. So there is this radius of the device in here. So therefore, the final speed is equal to the cyclotron frequency multiplied with the final device. So that's the final speed that you can achieve with this. To build a better device that accelerates the particles to even higher speeds, you either need to increase the radius or the magnetic field, right? That explains why at CERN you have an accelerator with a very large radius, it's about of the order of kilometers basically, because you cannot increase this magnetic field in here very much because we have some other issues for producing magnetic fields. But of course, that's one way of doing it, but there's actually a certain limit that we can achieve. Right, let's just finish this with final thing. Lawrence was able to accelerate protons by using this device in 1930s. And he actually accelerated them to almost relativistic speeds. That was actually a very good result. But of course, to be able to accelerate the protons, the particles, even further, they need to change the design in here. And the main reason is that we have said that the cyclotron frequency, which is given by this expression, is not actually correct. It's only an approximation, so there's some kind of a relativistic effects that also changes this value. It appears that the correct cyclotron frequency actually depends on the speed. So there's some kind of a factor in here. So that's the correct expression of the cyclotron's frequency. So that means at high speeds, when the particle reaches speeds comparable to the speed of light, the cyclotron frequency actually decreases. And because of that reason, you cannot use this design to accelerate particles once they reach speeds comparable to the speed of light. So as a result, you have to do something else. So the synchrotrons are devices that do that something else. They actually use lots of different techniques for actually increasing this the final possible kinetic energies. As I have said, one of them is to increase this radius of the device, but that's something else. But the essential idea of all the cyclotrons are essentially the same as of all the synchrotrons, the modern accelerators that we use. It's more or less the same as the design principles of the cyclotron, right? Let's repeat again. Of course, the frequency depends on the speed, but for all relativistic, non-relativistic speeds. So let's say it like this. If the speeds are smaller compared to the speed of light, in that case, omega c is approximately equal to qv over m. That's independent of energy. So that's the main principle that we use for building the cyclotron, because let's remember the idea in here again, because we would like this frequency of that AC EMF device to match exactly the frequency of the particle's motion in here. Only in that case we can keep pumping energy, kinetic energy, to the particles.